we're going to use geometry one more time to try to get us this alternate version. Now, the geometry that is useful here is something called the cosine law. If you've got a triangle like this that's very general, and there's some angle here, and we're going to call this length A, B, and C, the length of the side across from the angle, that's going to be C squared, is A squared plus B squared minus 2AB cosine of theta. We're going to translate this into a vector version. So if I have the vector A here and the vector B here, if you were to take the negative of a vector, it just flips its direction. The parallelogram rule tells me that this is A minus B, and because we're free to translate vectors, that means that the length of this, or the vector here, this third side, is A minus B. Here, the length A is just that, B is just the length of this vector, and C now ends up being the length of this vector A minus B. The cosine law translates into A minus B as a vector length squared is A squared plus B squared minus 2 length A, length B, cosine of theta. Well, hey, this quantity right here is exactly the dot product. So we end up with a nice formula that tells us something about the dot product in terms of these other quantities. If we have our vectors with components A1, A2, and A3, and B is B1, B2, and B3, we can calculate the components of the difference. This is just A1 minus B1, A2 minus B2, A3 minus B3. The length of a vector squared is essentially A1 squared, A2 squared, A3 squared, square rooted, and then all squared, so effectively the square root goes away. I will get this quantity here, but the key to all of this result, length of the difference squared, I'm going to get A1 minus B1 squared, A2 minus B2 squared, A3 minus B3 squared. Now the squares are all on the outside here. I have to clean this up by foiling it out. I'll get A1 squared minus 2A1 B1 plus B1 squared, and the same thing will happen to the remaining terms. The exact same pattern happens. It is going to look like a mess, but you'll see in a moment that it will all clean up nicely. All of these things here are on the left-hand side of the equation. These things right here are on the right-hand side of the equation. So on the left-hand side, I'll have A1, A2, A3 squared, B1, B2, B3 squared minus 2A1 B1 minus 2A2 B2 minus 2A3 B3. On the other side, I'll have exactly these same quantities and that dot product term that I'm interested in. 2A dotted with B. These terms cancel. These terms cancel. And after a lot of work, what I'm finding is that negative 2 bunches of this end up giving me negative 2 bunches of the dot product. So at the end of the day, I've come up with a very handy result. It's possible to compute their dot product without having to know the angle between them. So this is sometimes called the definition of the dot product, but I'm going to call it the algebraic definition of the dot product. And it provides us with a very simple recipe by which to calculate dot products. If I give you a vector u, let's say root 3, 1, 0, and a vector w, 1, root 3, and 2, root 3, I have no idea how these vectors look relative to each other. And the question that I want to find here is I want to find the angle between these vectors. Well, luckily we can combine both versions of the dot product formula we've got. This is going to be u w times the cosine of the angle between them, and this is the part that I'm looking for. The length of u is straightforward. It's going to be root 3 squared, 1 squared, 0 squared, which is going to end up giving me a root 4, which is 2. The length of w is going to be 1 squared, root 3 squared, 2 root 3 squared, which is going to end up giving me a 1 plus a 3. 2 squared is 4, root 3 squared is 3, so 4 times 3 is 12. So this is going to be a root 16, which is a 4. Now, the key to all of this is that I've got a formula to calculate dot products. And that means u dotted with w is going to be the first component of u times the first component of w, the second component of u times the second component of w, the third component of u times the third component of w. And so this ends up giving me a root 3, and a 0, so I get 2 root 3. Cosine of theta is going to then be u dot w over the length of the product of those two. So I'll get 2 root 3 over 2 times 4. And that means that theta would be the inverse cosine of root 3 over 4. Now remember, theta has to be between 0 and pi over 2. So this, if you use a calculator, is about 1.12 radians, which is about 64.3 degrees. This version of the dot product is also helpful because it allows us to prove many properties about the dot product that are extremely useful. If I were to take the dot product of two vectors, and I'm just going to assume we're in R3, this is the standard way to calculate their dot product. All of these components are just real numbers, and all the rules of real numbers apply to them. And that means if I have a product, I can switch the order of the product individually, and you can see for yourself that the order in which you compute a dot product is irrelevant. You're free to switch the order of those two things around. Now, we've already hinted at this a little earlier. If you were to take the dot product of a vector with itself, what you would find is that this is very closely related to the length of the vector. And in fact, this ends up being the length of the vector squared. So another way to think of the length of a vector is as u dot u with the square root. If I have a constant with a dot product, I can simply use the definition of this dot product and use the properties of real numbers. So if I wanted to, I could distribute that c to each term and then rewrite each one of those terms as follows. And this is exactly the same as if I would have taken the vector cu1, cu2, cu3 and dotted it with the vector v1, v2, and v3, which ends up being the same as cu dotted with v. If I wanted to do the exact same expression, I could have chosen to distribute the constant on the v. So I'm hoping that you can see it doesn't really matter where that constant goes. There's a distributive property that we also have. The dot product says take the first entry of this vector and multiply it with the first entry of that vector. Well, that's going to give us a u1. This is v1 plus w1. And if I go down the line, this is what I end up with. We can now use distributive properties of real numbers. So we'll have a U1, V1, U1, W1, U2, V2, plus U2, W2, plus U3, V3, plus U3, W3. I'm free to reorganize this as U1, V1, U2, V2, U3, V3, plus U1, W1, U2, W2, U3, W3. This is the same as U dotted with V plus U dotted with W. So we end up with a nice distributive property of dot products. This vector can be distributed. These properties are very useful because they allow us to prove a lot of facts. For example, let's talk about simplifying an expression that looks like this. The key idea here is remembering that when you've got the length of a vector squared, you need to think of it as the dot product of that vector with itself. And this opens the door for you to be able to use different properties of dot products. The first property we're going to use is this distributive property. So this allows you to distribute the first vector onto the others. You can switch the order of the dot product. It doesn't matter. You will get the same result at the end of the day. That allows you to use the distributive property again. And when you've got that, you'll end up with a U dotted with U, U dotted with V, V dotted with U, V dotted with V, which these two terms can be combined. This simplifies to the length of U squared. This will give you two bunches of the dot product. This will give you the length of V squared. This is the vector version of foiling. So the length of U minus V squared is very similar to the one we just did above, except the minus sign will cause us to think just a little more. The key takeaway here is that the distributive property allows us to go through over this. Now, the other thing we want to remember here, this is the same as U plus negative V. And that negative is really a constant. So we'll get U minus V dotted with U plus U minus V dotted with negative V. We can switch the order of this dot product. I'm going to write that second term as an addition with a negative V. This will be a negative V dotted into U plus negative V. I'll end up with a U dotted with U, U dotted with negative V dotted with U, and negative V dotted with itself. Anytime we have a minus sign, we're allowed now to take it out. So we'll have the following. And we continually use these properties to get to these results. Negative 1 squared is just 1. So at the end of the day, this ends up giving me the following. So I know it's been a lot of work, but the point here is that we were asked to simplify this expression. So what we end up getting is two terms that look almost identical, except there is one important difference between them. These middle two terms have opposite signs, so they will cancel out. Two bunches of U squared length and two bunches of the length squared. Now this is something called the parallelogram equation. Here's my vector U and here's my vector V. If I were to draw a parallelogram, This right here, I know that the diagonal is the vector u plus v. This vector down the diagonal there, that would be u minus v. Now, because I'm free to shift and translate vectors wherever I want, that's a u minus v. The parallelogram equation says the sum of the lengths of the sides squared, you're going to get 2 bunches of u and 2 bunches of v squared. That's going to be equal to the length of one diagonal plus the length of the other diagonal. Dot products are an incredibly important tool that are far-reaching in mathematics. We're going to practice them throughout the whole semester.